Okay, so we're going to do one more simulation example this week, and then your homework assignment is going to be doing some initial DC simulation examples. And then next week we're going to get into doing some AC examples, although I might take that back. We might do DC some more, but with some capacitors and inductors. We'll see what I feel like doing next week. But we'll have another week or two with simulation, and then we're going to really kind of transition ourselves into the bulk of this course, which is going to be um, learning how to do layouts. So I'm going to go ahead and do the assignment that is posted with this video here. So I'm going to first start a new project, and this is on my computer now. I'm not using the web interface. I'm using just my regular computer. And I'm turning my audio down a little bit because I'm actually listening to music while I make this, which my wife tells me is a bad idea to do, but I still do it. Um, so we're going to call this just week 3, example 2. I'm doing the PSpice mixed analog digital. Click OK, create blank project. Now, surprised using my computer is much faster than this. Probably have too many windows open. All right, so I bring my parts tab open again here, and I want to just show you that on my computer here, because I've used this many times, it leaves all the libraries that I've already installed on here. So if you're using the labs, the computers in the labs in 211, 209, or 204, they're probably already going to have all the libraries installed that you need. They're going to have the analog and the source library, which is what we're going to really need at this point in time. We're also going to, there are some other libraries like op-amp and other things like this that maybe we'll look at a little bit later in the semester. But right now, I just need to do the analog, and I'm going to do my resistor. And again, these resistor values in this example are small. And the homework assignment, I'll see what values I use. When we get into real circuits that are actually do real things that we are going to lay out, the resistor values will be a little bit different and a little bit more what we would consider realistic. And so again, I'm just placing all of these resistors kind of in the same rough configuration that is in the picture. I'll zoom in a little bit. And then I'm going to place my source. Now, one thing you can do here, instead of scrolling down, you can just type in VDC. If you know the name of your part number, you can just type it in at the top and it jumps right down to it, so you don't have to scroll through it, which actually can be helpful in some of these libraries. The source and the analog library don't have that many components, but let me see here, just if if you see, like this one's even not that bad, but it's got a lot of different parts in there. Yeah, even these libraries aren't too bad as far as the number of components, but some of them you can get it so that there are just tons of components in there. All right, make sure to add a ground, 0 capsim, and then I'm going to go ahead and change all my values here. So this is 5 volts. Do that by double clicking, of course. 4. Typed in the wrong number. And this is also for 2. 2. And now I'm going to use the W key to then start connecting up everything. And connecting everything up. Okay, so everything's connected now. Now I'm ready to do my simulation profile. And I'm going to call this DC again, just because that's what we're doing. And mine has already popped up. You can see how much faster it is when you're not connected. And, even though the computers in labs can be a little bit slow, but they're still so much faster as far as connecting to that license server. And so I'm going to say OK, because we don't have to change anything for a DC simulation. And then I'm going to go ahead and simulate. And then my simulation window has popped up and I'm 100% done. So again, much faster doing this than if I did it online. Now I'm going to go ahead and turn on my voltages. And it asks for voltage across each resistor. So the voltage across each resistor, where's my text box here? Just do T here for text. So for R1, it is equal to, and I'm going to go ahead and write the numbers down, but I am fine if you just put your answers only on the assignment. So R1, here I should maybe do this. VR1, the voltage across R1 is 5 minus 3, which is 2 volts. And I hit the wrong key. So let me try that again. And then VR2 would equal 3 minus 2, which is 1 volt. VR3 is equal to 2 minus 0, which is 2 volts. VR4 is equal to 3 minus 500 millivolts, which would be 3 minus 0.5, which is 2.5 volts. VR5 is equal to 500 milli minus 0, so that is equal to 500 millivolts. And then VR6 is equal to 500 milli minus 250 milli, which is equal to 250 millivolts. And finally, VR7 is 250 millivolts minus 0, which is equal to 250 millivolts. And so I'll just place that right there. And as a side note, if you want to do something like this in the simulation as part of your answer, that's fine too. And again, I'm okay if you write answers only on this particular type of assignment. Now the next thing it asks us to do is the current in the simulation agreeing with what Ohm's law tells us the current should be? And one thing I want to make sure that is clear here, and I'll show you an example of what people do wrong sometimes, is that Ohm's law is, we know it's voltage is equal to current times resistance, but it's the voltage drop across the resistor. So if we want to verify it, for instance, that's why we kind of did all these computations here at the first here. So to verify that this should be 500 milliamps, for instance, I would have, well, the voltage drop across IR1, so I'll have current for IR1. And now I do want to see a computation for this, because otherwise you just turn the simulation on and you can see that it works here, is that I want to see, okay, well, it's 2 volts, and then you can just do the equation, kind of like rearrange it in your head, because it'd be 2 volts divided by my resistance to get me current. So 2 volts divided by 4 ohms, which is equal to then 0.5 amps, which is, of course, the same thing as 500 milliamps. So it is confirmed that on this particular resistor that Ohm's law does agree with what our simulation tells us. And the reality is it better agree, because, I mean, this is just a basic simulation, and if this doesn't even work, then none of our other simulations have any hope of working correctly. So that's good. And then, of course, we need to verify it on all of them. I'm not going to take the time to verify it on every single one, but I want to point out one thing here, is that if sometimes I see people making a mistake where they'll either say that the current through R1 is maybe it's like 5 divided by 4 ohms, because they use this 5 volts here. Or sometimes I see them saying that it's 3 divided by 4 ohms, because they're using this voltage here, 3. Remember, those voltages are voltages at points, and they're always measured with respect to ground. They're always measured with respect to this ground here. So it's like taking a voltmeter and putting one probe here and then one probe down here. That's why we're getting 3. But the voltage across the resistor is 5 minus 3. Now, there is a way that you can actually measure the voltage across the resistor without having to do that subtraction. And that's how I'm going to show you how to do that. Is I'm going to show you what this other screen can be helpful for at times. It will be more helpful when we're looking at AC signals, but you can even use it at this point. And what I mean here is that there's these little probes here. And one of them here is a voltage level marker. So if I click on that, we'll see I have this little probe thing. And now you have to be careful when you click. Like if I try to click right here, it'll give me an error. It says, hey, you need to connect it to a wire, bus, or a pin. And I'm like, oh, okay, so let's connect it to a wire. So I'm going to connect it to this wire. So it's green. So that means that I'm going to have a green line here. And as a side note here, what I did is I right-clicked on it to make it bigger. If you were to ever print these out, you'd want to change some color properties here, because otherwise what would happen is if you printed this out, it would print everything in black, and then it would be really hard to read. I'll talk about that later at some point on how to change it, because right now, if you were to put this in a document and submit it online, that's fine, because I'm not printing them out. I'm just grading them right now by looking at them online. But if we're going to print these out, I'd want you to change it so that the background was white and that these grid lines were black. And then the lines could be whatever color you want it to. And I just made the line thicker just to make it easier to see. But the point is that it's 3 volts. Now, what's this x-axis here? This is time. Well, it's saying that, well, it's always 3 volts. And that's because that's the DC voltage. So the DC voltage doesn't vary with respect to time. Now, we're going to get into AC voltage and AC current, and that does vary with respect to time. And we'll look at that when we get to simulations. But I also want to show you, if I take a current marker, I could put that, if I tried to put that on a wire first off, it says it's got to be connected to a pin. And a pin, it can be any part of these components here on the edge. So I'm going to connect it to the edge of R4 here. And so now I've got here another value trace showing. Now, one thing that you have to be careful with, and this is sometimes it's not good to put both voltage and current on the same graph. And the reason is that notice there's no units on this graph here, because it's basically saying, well, this line's at 3, and you just need to know that the green line is voltage, so it's 3 volts. And this line is at 0.25 or 250 milli, and you just need to know that it's current in amps. So typically it's not good to plot both of these on the same graph like I did. You either plot all your voltages on one graph and then all your currents on another, or something of that nature. But for demonstration purposes, I'm going to go ahead and put multiple measurements on there. Now I'm going to put another current probe on here. I'm going to put it on the other side here, and that becomes blue. Now, if I look at that, and I'm going to make that line thicker for us to see, that's negative 0.25. Well, that seems odd. Why is it negative if the current is 0.25? Because that's what it says here. And it has to do with the direction. So if we're looking at this probe here, and this number, 250 milliamps, that's the current flowing from the left side of R4 to the right side. And that's positive. So that means there's a positive current going from left to right. Now, putting this blue pin here, it's saying, okay, well, what's the current going from right to left? And this is really kind of have to think of vectors. And it's like, well, if the current going from left to right is positive, then the current from going from right to left is negative. It's just a different way of writing the same answer. But that's where you have to be careful sometimes with your positive and negative numbers here. And so you might say, well, the current can't be negative. Well, first off, current can be negative. There's no problem with that. Current is just a direction. But if the current is negative going to the left, what it really means is if I'm wanting to think about positive current, that the current's actually not going to the left, that it's actually going to the right. And by definition, these DC currents that I can turn on and off are going to always give you where the positive current is flowing. All right, so let me take a couple of these off here. And if you delete these probes by just selecting and deleting them, they disappear from the graph. One more I want to show you here. The last one I want to show you here is this differential probe. It's the second one in here, voltage differential markers. These you have to put at 2 points. Now if I do this and I put 1, and notice it has V plus here, and then a V minus on the other side, and it's red, so I'm going to go back and look at the red curve here now. And it's not letting me really select this very well. But it's, of course, if we can, it's the one on the very bottom here, but it's 2 volts. Well, wait a minute, 2 volts is the voltage across it. So that differential probe will let you measure the voltage across a component. And you have the positive side is always where you put the first one, the negative side is where you put the other one. Now, just like with current, if I did this in the opposite direction, I put the positive here and the negative one here, we're going to get -2 as this blue curve down here as the voltage. But that's just simply because I've flipped the direction of the probe. All right, so that should be good enough to wrap us up with everything that we need to know for this week's assignment. And so we'll get into some more advanced simulations next week. Please make sure to email me if you have any questions regarding anything from this week.